So I will talk about the Hornamossen Benchmark, and this is a site in Sweden. It's a typical wind turbine site in Sweden, meaning that it has some topography, not too complex, but a very complex forest cover, because the predominant way of the predominant forests in Sweden, they are all clear-cutted, so they are full of stands of different age and density, basically. So just to give you some background, we had already a first benchmark in Sweden for another site, and that was not as large measurement campaign and less complex, because there was basically no topographical complexity, just the forest cover was quite complex. But what we learned was that the footprint characteristics really can be seen in the profiles. So that means that the domain of the model domain needs to be quite large in order to accurately capture differences in different wind directions. And also that due to that, the results become dependent on the turbulence intensity, or rather the mixing over the advection, or the ratio between the mixing and the advection. So in order to get a proper description of the flow physics at the site, then we need to have a realistic distribution of that ratio between mixing and advection, meaning that we need to include stratification and ideally also transients, just due to the complexity of modeling, for example, unstable or stable conditions in a stationary condition. Therefore, we argue that it's better to do it in diurnal cycle. So the aim with the Hornamossen benchmark is then to test the model chain of NEVA and see how it performs in complex terrain with heterogeneous forests, and also to do that in relevant atmospheric conditions, as opposed to this earlier benchmark which only used neutral conditions. So we'll give a brief overview of the site. There is also more information on the site itself on the Windway blog, so you're very welcome to go in there and ask and give comments. The site is located in the southern part of Sweden, just east of the second largest lake, and the distance to the lake is 15-20 kilometers. The predominant wind direction is southwest-southwest, and the upwind forest, or the upwind ground cover, is basically forested in the total fetch. The site was instrumented like this, so we had a few different profilers, mainly AQ system SODARs, but apart from that, we also had a few different lidars. So we have two Sapphire lidars, one at the tower location and also one at the westernmost location. Then a couple of SODARs, and we had a station in at lower elevation, which had a ceilometer as well to assess the boundary layer height, and long-range wind profiler. And in addition to that, we also deployed this system of 4 microbarographs in order to try to deduce the static pressure gradient to get a measure of the geostrophic wind speed, because we realized that it's good to have as good control as possible of all the inflow or all the boundary conditions that you use in modeling. So therefore we decided to try to measure the static pressure gradient. So the tower in the middle, it's 180 meter high, and it was equipped with 8 levels of sonics, quite a lot of cups, both heated and non-heated, and vanes, of course, so more typical wind energy setup, but also a very detailed temperature profile and 2 levels of 4-way radiation stage sensors in order to assess the quality of the WRF data that we use as input for this benchmark, but also to try and find out more about the actual flow physics at the site. So after studying we had the measurement there for half a year, and it was from spring 2016 to autumn 2016, and it became clear that there were few periods where all the instrument worked, but we could find or identify 2 periods, one with westerly flow and one with easterly flow, where the conditions were semi-stationary, so they were kind of the same for a number of days. And what was good was that they are almost these periods are almost barotropic, so that means the geostrophic wind doesn't change with height, and they were mostly clear, so well, not too complex to model. And the idea behind that was that we wanted to have as little phase problems as possible between the mesoscale data and the actual model data. So here you can see 2 movies of the 2 periods, the western case and the eastern case. And the western case is in early August, and the eastern case is in early June. So both of them are in the summer, which means that there is a bias towards unstable conditions in these periods. But the good thing is that there were still a couple of night hours. So if you look at the distributions of the stratification, we can see that all the data is the black distribution, which is biased towards stable conditions. And you can see that both the east wind case and the west wind case in green and red are biased towards unstable conditions. But the width of the distribution is still quite wide, so that we expect to be able to see a variety of stratifications come into play. And the blue vertical bars there are just the definition of neutral that we used for the selection of data for the previous benchmark. So you can see that the conditions for this current benchmark is much wider. So to get into some more details about the cases, this is the east case, and as you can see, the direction is quite stationary and stays at around 90 degrees, while the 100-meter wind speed varies a little bit. But we plan to normalize the data with the 100-meter wind speed from the tower. So as long as the stratification is roughly the same in the model and the measurements, we expect to have the similar fetch from both the measurements and the model results. And you can see that the first day is basically clear sky conditions, while the third day has a little bit more clouds. For the west case, we have also a stationary period with the wind direction very persistent at westerlies, and the wind speed is also rather stationary, but we have more clouds. So if you look at the radiation, it's a little bit more wiggly. The curves wiggle a little bit more, but that's what we had to live with. These were the 2 best periods that we could find. So I also wanted to include something on this idea of using the mesoscale data as model input. So in the original plan, we thought that it's better to use the tower data as boundary conditions for the models, so that we make sure that there is no problem by any false bias due to differences in the modeled and the measured background conditions. But we also have this desire to test the model chain in the new European Wind Atlas experiment. So, and this is a good opportunity for that. So in the end, we decided it's better to use WRF data, and that also has a good coverage, and you can get more things from that than from just the measurements. So I spent some time analyzing the WRF data at this site and see if it was acceptable to use it as inputs for the microscale models. So what you can see in this graph is the east-west geostrophic wind, and the red line is from the WRF simulations, and as a gray line you can see the geostrophic wind from the pressure gradient system at 1 hour average, and you can see some spikes there. It was quite difficult to get good quality of those data. Basically, we had, I think, with hindsight, put the barographs too close to each other. But if we and they had some problems with the changing temperatures. So therefore, if you use a 24-hour average, which evens out the differences between day and night, then the curves look more smooth, and they follow quite nicely the simulations from the WRF model. And if you look at also the 180-meter tower wind speed, you can see that there is a good correlation with that as well. And this this gray box singles out the period that we have chosen for the experiment. So this is the western case then. So when it comes to wind direction, as I said, it's quite persistent, and there is also a good agreement between the modeled wind direction, which is here for the 180-meter height, it's represented by an orange curve, and the measured one, which is represented by a blue curve. And that's good because that lets us assume that the footprint should be roughly the same. When we look at the heat flux, the magnitude of the heat flux is rather well predicted, actually. Of course, there is more scatter in the measured heat flux because of the the lack of small scales in the WRF model, but the magnitude of the diurnal cycle seems to be well predicted. And if we look at the radiation, this is only the incoming shortwave radiation, and there are two blue curves, one for the 5-meter level and one for the 30-meter level. But the take-home message is that the magnitude of the incoming radiation is well predicted, and also that even though the curves aren't that smooth, the variation in the curves is similar for this period. So the only thing that popped out from this study was that there is a significant cold bias in the model, so that the temperature is quite a lot lower in the model than in the measurements, but the temperature profiles they were quite okay, so it's just a cold bias. To sum up this benchmark, there are 2 days, and they each cover 3 days, and there are periods they were chosen to avoid phase errors mainly, and to have barotropic conditions, so to simplify the evaluation between the model results and the measurements. And you can find the input data from the WRF model on the Windbane blog. And also there is a 40 by 40 kilometer patch of forest densities as well as elevation heights that we have derived from airborne laser scans. So and that's the main thing, that we can actually get the forest into the microscale models as it is in reality, so that we expect that when we have the same wind direction, we have actually the same footprint. If you have any, if you want additional information, you can find it at the Windbane blog, both for this particular benchmark and for the site as a whole. And we also want your results before 31st of January 2019, and also plan to show the first results at the Wind Europe Summit. yes, thank you for listening to this. If you have any questions or comments, I'll happily answer to the best of my ability. You can also email me at this address. And I would like to conclude by acknowledging the big contribution on this measurement campaign and work by NEVA, but also by the Swedish wind research organization Windforsk, which financed the tower measurements, and Stand Up for Wind, which is a research organization for wind in Uppsala and Stockholm in Sweden.